you're beginning to get to grips with the idea of functions. Remember the essential features of a function. It's got a domain, a codomain, and a rule. And the rule tells you where everything in the domain gets sent to. But why should we make such a fuss over domains and codomains? This program's all about inverse functions, and that's when you're trying to reverse the action of a function. And when we do that, domains and codomains become quite critical. But why should we be interested in reversing a function? Well, over here, I've got a model of a ballista. A ballista was the weapon used by ancient Romans to knock the heads off ancient Britons. But we'll just restrict ourselves to trying to knock a football off a post like this. Now, the ancient Romans weren't really great technologists. You see, the trouble with this device is that it fires a ball always at the same angle with the same speed, and so it goes along the same trajectory every time. If I wanted to describe the ballista mathematically, then all we've got to do is to find the trajectory. And then, for any given distance, we'd know the height that the ball passes through. But the Romans' problem was rather different. They didn't have a fixed distance and wanted to calculate heights. Their target was fixed. So what they wanted to do was to find out where to place the ballista for a given height. We're looking for the trajectory of the ballista, and we can think of the trajectory as the graph of a function. But what function? The graph's a curve. So let's try the simplest curve we know, x squared. That's no good, it's the wrong way up. Try minus x squared. That's better, it's the right shape, but in the wrong place. But with a bit of translating, vertically, and horizontally, then it matches. And we've used this equation in the text. It can be rearranged to give 4x minus x squared. So now we've got a function for the trajectory. The domain's the interval 0, 4. Codomain, well, that's just r. And we've also got a rule. So we can choose any value in the domain, and the function will specify the height at that distance from the ballista. But we want it the other way round. Given this height, we want to be able to calculate the distance. We want a function that goes the other way round. Well, I can't see immediately how to find the inverse of this function. In fact, for this height, I can see two values for the distance. And that's no good at all if I want a function. The problem arises, you see, because this function isn't 1, 1. So to see how to approach this reversing problem, we'll look at a similar function that's not 1, 1, but which is simpler.
The function Norman had was a quadratic. Now, the simplest quadratic is x squared. So can we find an inverse for this function with rule x maps to x squared and domain and codomain the whole of R? We'll start by tackling the problem graphically. The inputs are on the horizontal axis, so if we take a number on this axis, then from the graph we find the output on the vertical axis. But we can input another number. But the graph gives the same output. So two different inputs give the same output. That means that the function is not 1, 1. So there's no hope of an inverse. If we try to go backwards, which value do we go back to? This function doesn't have an inverse, but there is something we can do. We can split this graph into two parts, and these graphs correspond to two new functions, and both of these functions are 1, 1. The left-hand graph we'll call L. It has domain with 0 and negative real numbers, which we'll call N, and codomain R as before, and the rule is the same. The right-hand side is a 1-1 function we'll call R. It has domain with 0 and positive real numbers. We'll call this set P, and codomain and rule are just as before. We'll begin by looking for the inverse of the function R. Graphically, instead of the arrows going this way, we want them to go the other way. And on the graph, that's no problem. And that's the first step. Now let's reverse the arrows in the process box. But that R's nonsense. We can't feed any real number into that process. We've got to restrict ourselves to 0 and the positive reals. That is to the image set of the original function. Now that image set is 0 and the positive reals. That is the set we call P. Now that completes the first step, reversing the arrows. But we don't usually write our functions going in this direction, nor do we draw our graphs like this, with inputs on the vertical axis and outputs on the horizontal axis. So the next step is to get the arrows on the graph correct by interchanging the horizontal and vertical axes. And we'll turn the process box round. So now all the arrows are going the correct way, and we've got a rule for going from input to output. We're just left with one small task. Our rule shows x squared mapping to x, whereas we usually have x maps to something. So that's our final step. In order to get from an input of x squared to an output of x, you have to take a square root. But there are two square roots, so which one do we take? Well, the output has to be in P. That is, it has to be 0 or a positive number. So we must take the non-negative square root. And now we can complete the final step and fill in the process box. The domain and codomain of the function are both P, and the rule maps x in P to the non-negative square root of x, which is also in P. This is the function we're looking for. It reverses R. It's called the inverse function of R, and it's written R to the minus 1. Now that's dealt with the 1-1 function we got from the right-hand side of x squared, but there's another 1-1 function, L, from the left-hand side of the graph. Given an input which is negative, we get an output in R. But we want to construct the inverse function. We want to go from x squared back to x, where x is 0 or a negative number. We also want the process box to operate the opposite way too. We start with numbers in the image set, that's the set we've called P, and we have to end up with numbers in N. And the rule for this is to start with x squared and get back to x. That's the first step, reversing the arrows. The second step is to get all the arrows going in the usual direction. Graphically, we flip the graph. And in the process box, we simply reverse all the arrows. The last step is to sort out the rule into x maps to something. The reverse of squaring is taking a square root, but the image set is n, so this time we must take the negative square root. That's the technique for finding an inverse of a 1-1 function. And even if you haven't got a 1-1 function to start with, it may be possible to split it up first into 1-1 bits and then apply this technique to each bit. So let's return to the ballista problem and see what we can do with its trajectory function.
The trajectory function isn't 1-1. For example, there are two values here which give us the same value in the codomain. But Bob's told us how to get around this. What we do is to split it into 1-1 bits. And the easiest thing to do here is that, to take the bit going up and the bit going down. Let's concentrate first of all on the bit going up. We'll call that function u. It's got domain 0, 2, codomain r, and of course the rule is exactly the same. Now, Once we start to mess around with this process box, remember the first thing that we've got to do is to replace the codomain by the image set. And in this case, the image set is the interval 0, 4. And then we can change the arrows round in the process box. What about the graph? Well, we'll have to flip the graph if we want to see the graph of the inverse function. That's easy enough. The inverse function has a graph that looks just like that. And now we can turn the process box round as well. The only thing that remains is this nasty looking expression on the left here. If we want to specify u minus 1, the inverse function, in the normal way, we want that ruled in the form x maps to something. We're stuck at this very last step. What we need is an algebraic technique to sort it out.
To illustrate the technique, I'll look at a simpler function h, whose rule is x maps to 5 minus 4x. What's the rule for the inverse? Now, the usual form of a function is x maps to something. How can we work out what to put in the cloud? The clue comes from looking at what you'd do if you were using a calculator. To get an output of 5 minus 4x from an input x, you'd start by multiplying x by 4 to get 4x. Now we want minus 4x, so you have to change the sign. Finally, we want to add 5, and that gives the result. This output we usually call y. Now, to find h to the minus 1, we have to reverse the process. We work backwards, reversing each step as we go. The last process on the way down was add 5. So our first process going backwards is subtract 5. So if we start with y, we get y minus 5. Next, we have to reverse change of sign. Well, just change the sign back again. And that gives minus y minus 5. Lastly, reverse multiply by 4. That's divide by 4, or multiply by a quarter. So the final output is minus a quarter of y minus 5. So the rule for h to the minus 1 takes an input y and gives an output minus a quarter of y minus 5. And if you input x, then your output is minus a quarter of x minus 5. Now, Norman, can you apply this same technique to the rule in your function?
Well, let's see. Where have we got to? We found the inverse function so far, and the outstanding problem is to express the rule in the form x maps to something. What we've got to do is try to reverse this expression somehow or other. So let's take a closer look at that. We've already seen when we were working out the image set, there's an alternative form for that expression. You can, in fact, write it in the form 4 minus x minus 2 squared. So let's see how it actually calculates the output from the function u if we input x. And remember, we've got to calculate this expression. Well, the first thing we want to do is to subtract 2. That gives us x minus 2. Then we've got to square it. That gives us x minus 2 squared. And then we want a minus sign there, so we'll have to change the sign. That turns that into minus x minus 2 squared. And finally, we've got to add 4. And then we get 4 minus x minus 2 squared, which is what we're looking for. And that's the output when we input x. And, of course, we usually call that y. Now let's see what happens to y if we reverse the process. If we input y into the inverse function u minus 1. What we've got to do is to reverse each of these steps. Well, the reverse of add 4 is subtract 4. That gives us y minus 4. Then we've got to reverse the change of sign. Well, the reverse of change sign is change sign again. If you change the sign of that, you get minus y minus 4. Now we've got to reverse squaring. Well, the reverse of squaring is square rooting. There's a bit of a problem here, because if you take a square root, you get two possible answers. So let's worry about that one in a minute. At the moment, I'll just put down plus or minus the square root of minus y minus 4. And finally, we've got to reverse this step, subtracting 2. Well, the reverse of subtracting 2 is adding 2. So we get two possible answers. We get 2 plus the square root of minus y minus 4, or we get 2 minus the square root of minus y minus 4. Now, how do we pick which one of those we're looking for? Well, have a look back up here. The codomain of u minus 1, the inverse function, is 0, 2. Now, if you look at this expression, we've got 2 plus something. That'll take us outside the codomain. So that can't be giving us the values that we want. It must be this rule that we're looking for. Let's just check it with a particular value. Let's see what happens under u minus 1 to something in this domain. Let's take the value 3. And what does 3 map to? Well, if I replace y by 3, I get 3 minus 4 here. That's minus 1. Minus minus 1 is plus 1. Square root of 1 is 1. So I get 1 there. I get 2 minus 1. I end up just with the number 1. Oops, number 1. So 3 maps to 1. Now, if I want to fill in this final expression here, x maps to what? All I've got to do is replace my y, which I was inputting here, by what I'm actually inputting, and that's x. And so I get 2 minus the square root of minus, and instead of y there, I'll get x minus 4. And that completes the problem. We've found the inverse function to the function u. So let's try it out in practice. Remember, the inverse function is a part of the trajectory of the ballista. So if we feed in a height, it should tell us the distance at which to set the ballista. So if the football is 3 units high here, then the ballista should be set 1 unit away. Let's try it out. That's very interesting, but it knocked the football down before when the ballista was right back here. And that means there are 2 positions where we can knock the football off. But remember, we split the trajectory into 2 and only found the inverse of 1 bit of it. If we'd used the other bit, then we'd have found the other position. And also, we'd have used the other rule, the one, remember, with the other square root. We now have techniques for finding inverses of 1-1 functions. And even if we don't have a 1-1 function, then we try to split it into 1-1 bits. Now, it turns out that many of the most useful mathematical functions that we have to deal with are not 1-1. And so a certain amount of splitting has to be done before inverses can be found.
Some of the most useful functions which are not 1-1 are the trigonometric functions. If a problem ends up with a cosine of the answer you want, then finding the answer itself requires an inverse procedure. To look at the inverse procedure for cosine, we'll start by reminding you of its graph. The cosine of an angle x is defined using a unit circle. So, by plotting this horizontal length, we can get the graph of cos of x. It's a lot more convenient if we rotate our whole picture. We can now plot this length graphically the usual way. Of course, we can also go in the other direction for negative x. We've just drawn a small bit of the curve. We could continue plotting indefinitely in either direction. The curve just keeps repeating itself. So the cosine function isn't 1, 1 with a vengeance. But I've got a calculator here which claims to have an inverse for cosines. I can put a number in, press inverse and cos, and it gives me an answer. What's this machine doing?
Well, we know that if a function isn't 1, 1, it can't have an inverse. But all's not lost. Remember, we always try to split it up into bits that are 1, 1. Here's the graph of the cosine function. We've squeezed up the scale a bit so we can see a few more cycles. And how do we split up the graph into 1, 1 bits? Well, there are lots of ways we could do it, but let's take bits that keep as much information as possible. In other words, whatever bit I take, I want the image set to be the interval -1 to 1, the whole of the image set of cos. For example, this bit's 1, 1, and it's got the full image set, values -1 to 1. So that's certainly one possibility. That function will have domain minus pi to 0. Or we could take the next bit. That again has got the full image set, -1 to 1, and this time the domain is 0 to pi. And finally, I could take this third little bit here. Again, we get the full image set, -1 to 1, and the domain this time is pi to 2 pi. Each of these bits is 1, 1. Each of them I can calculate an inverse for. And the graph would just look like that one for this one. And if I reverse the process box, then I get that. This one will have graph that looks like that. If I reverse the process box, I get that. And finally, I could twiddle the graph of that one, reverse the process box for that one. So here are three possibilities for the inverse. But when you use a calculator, it only gives you one answer. So let's see what happens if I actually try to calculate an inverse cosine and see which one of these the calculator is using. Let's put in 0. We've got 0 radians. Inverse cosine gives us about 1.5, which is right in this range. So it looks as though this is the function that the calculator is using. And it is, in fact. And by international convention, when you ask a calculator to calculate an inverse, it always uses this particular one. And it's given a special name. It's called the arc-cos function.
So that's how we deal with cosine. The other trig functions are not 1, 1 either, but they can be treated similarly. In the text, we look at sine in detail, and to finish this program, we want you to look at tangent. The graph of tan is also constructed from a unit circle. This time it's the length along a tangent that we want to plot. Once again, we have a function that's not 1, 1. But we can split it up into 1, 1 bits. And each of these bits has an inverse. One of these inverse functions is arctan. We'll leave you to check on your calculator which one it is.